Hi everyone, welcome to the talk on modern browser security, the first line of defense, presented at AusCERT2020. A quick introduction about myself. So my name is Prateek. I'm a security researcher and I'm interested in mobile and browser security. I blog at highaltitudehacks.com. I'm also the author of a damn vulnerable iOS app, and I've spoken and trained at conferences such as Black Hat, DEF CON, Hack in Paris, Positive Hack Days, etc. And you can find the GitHub link to my GitHub repository over here. So let's talk about what we're going to discuss today. So we're going to discuss a little bit about the browser architecture. Then we'll discuss some JavaScript internals, followed by some of the latest browser mitigations which are being applied in the browsers today. We'll also look at attacking JavaScript core, which is most commonly attacked part of a browser these days. And then we'll look at how to build exploit primitives, and using those exploit primitives, how we achieve arbitrary read-write. Finally, we'll conclude with some advice on fuzzing WebKit. So why do we need browsers? Well, browsers have a huge attack surface, and the data is actually loaded and rendered from the internet. So you don't need, there is no challenge in basically getting code execution, because the data is itself loaded and rendered from the internet. It's also almost as complicated as an operating system in terms of the lines of code, and this basically gives it a big attack surface. It has a lot of entry points for remote code execution, which we'll see later in this talk, and it also has something called JIT compilers, which makes for a very easy target simply because it has a mapping which is read, write, and executable. It also has relaxed code signing, which means the code which is being run in a JIT region is not checked for its code signature. Let's talk a little about browser architecture. So the first thing to discuss here is the user interface. So the user interface is a component that allows the end users to interact with all visual elements available on the web page. This could be the address bar, the home button, the next button, and so on. Then we have the browser engine, which is a core component of every web browser. This actually acts as an intermediary or a bridge between the user interface and the rendering engine. It queries and handles the rendering engine as per the inputs it receives from the user interface. Then we have the rendering engine, which, as the name suggests, is responsible for rendering a specific web page. We also have a networking layer, and we also have a JavaScript interpreter, which is more important from an exploitation context, because it is responsible for parsing and executing the JavaScript code embedded in the website. So we'll look at how we can exploit this. Then we have a UI backend, which uses the user interface methods of the underlying operating system for UI stuff, for example, like drawing widgets and stuff. And then we have a persistent layer, which is a data persistence layer, which is used to store data locally, for example, cookies. So in this talk, we are mostly focused on the WebKit, which is the rendering engine of the browser. So what is the rendering engine? So the rendering engine is responsible for displaying the requested content, could be HTML, CSS, JavaScript. We are mostly interested in finding vulnerabilities in the rendering engine because it has a huge attack surface and many past vulnerabilities. It's also open source for all the major browsers, and also debuggable. So you can build a debug version of the of the rendering engine and debug it. So the rendering engine used for IE is Trident, for Firefox it's Gecko, and for Safari it's WebKit. The Chrome and Opera, they use a Blink, which is a fork of WebKit. It's important to know that all these rendering engines are open source. So if you actually open Safari and you open different tabs, you will see that all these tabs run as their own process, and the name of the process is web content. So this is a way to implement a same origin policy within the browser. However, the different tabs can also communicate to each other using IPC. So we'll look into this later on, how we can bypass same origin policy once we get read-write executable, read-write primitive within the context of the rendering engine. And this is how the render process will look like. When you run ps aux command, you will see all the tabs have their own process, and the name of the process is web content. So WebKit is the open source web browser engine, which is powering Safari on iOS and macOS. It's open source and it's some of different projects such as Web Core, JavaScript Core, and Web Template Framework. So the JavaScript core is the JavaScript engine which is used to render JavaScript code. In this presentation, we will be focusing mostly on JavaScript code. Now the code, the browser that we have on iOS and macOS, which is Safari, it basically wraps WebKit with some OS or iOS specific code. So with some platform specific code. We have something called WebKit ports, which is a combination of some platform technologies that allow it to run the WebKit browser engine. So to give you an example, the WebKit is used in several places. It is used on the PlayStation devices, it's used in Tesla. So the ports allow you to build WebKit specific to that platform. Now these are some instructions on how you can set up WebKit. So you just clone the repository and then you can check out to whatever revision you want. You can either check out WebKit from SVN or you can download it from GitHub. So the copy on GitHub is not the official one, but it's a copy. It's an unofficial copy of the repository which is hosted on SVN. Then you can either configure WebKit for the debug environment or for the release environment. You can also build WebKit with some address sanitizer support, which will help you to detect memory corruption vulnerabilities. Then you can either build the entire WebKit or you can just build the JavaScript component of the WebKit. So if you want to find out which particular version of WebKit is used in Safari, you can go to this particular place in Safari. So you just go to Safari and click on About Safari, and you can find this string here, which denotes the WebKit version which is being used. What are the advantages of building WebKit for debug versus release? Well, the debug build has it's slower to build, but it has the symbols. However, it also has some asserts which might block exploits. The release build is faster. However, it is not good for debugging simply because it doesn't have the symbols and stuff like that. However, it is good for testing the final exploit. So these are some instructions on how you can build. So in this case, I'm building, setting the WebKit configuration to support address sanitizer, and then building it with the debug flags, and also only building the JavaScript core component. And once WebKit is built, you can run it using the following command. In JavaScript core for the debug build, you have something called a describe function, which you can, as you can look here, it gives you the address of that particular object. And this is a very useful function which we will look at in the coming slides. You can also see that the structure ID is being incremented by 1 over here. However, with some recent mitigations, this has been fixed. So we'll also look at what is a structure ID and how this can be exploited. Then you can also, you should also understand how to convert unsigned long integer to raw double. Simply because in JavaScript core, when you store doubles, it's stored as an unsigned long integer. So these are some instructions on how you can use Python and use the struct module to convert a raw double to an unsigned long int and vice versa. So talking about JavaScript, so all the modern browsers are using JavaScript, and it has two different kinds of data types, one of which is the primitive types and the other one is the object types. Now different browsers implement their own JavaScript engine. So for example, for Safari you have JavaScript core, and for Chrome we had V8. However, the vulnerabilities exploited are very similar. So for example, if you have a type confusion vulnerability in JavaScript core, the exploitation would be very similar to let's say attacking the same, let's say exploiting the same vulnerability on V8. So primitive types have immutable data types, so they cannot be changed. So there are 6 primitive types: Boolean, null, undefined, number, string, and a symbol. So a primitive is basically an object which has no methods of its own, and they're also not mutable. So these are the 6 types which are considered to be primitive. Then for object types are something that are mutable and their values can be changed after getting created. So an example for an object type would be, let's say, an array. The properties in JavaScript can be either indexed or named. So if you want to fetch an index property, use the square brackets, whereas to get a named property, use the dot sign. So this is how you can fetch indexed versus named properties. In JavaScript, you have also have functions. So in functions are considered as objects in JavaScript. So which means you can assign functions to variables, to an array element, or to other objects. They can also be passed around as arguments to different functions. So I've given some examples on how you can use a function to pass it around as an object. Then we have something called function overriding, which is basically overriding a specific function of an object. So for example, every object has a toString function that can get invoked whenever it is being converted to a string. For example, if you're adding two strings and one of the added values is a number, then before addition the toString function will be called on that. So you can override that method by defining its own toString function, and once the addition happens, the toString function will get invoked, and whatever code you put inside that will be called. Okay, so for example, in this case we are overriding the toString function of the dog object. This is how do you debug JavaScript code. So debugging of JavaScript code can be done using either LDB or GDB, depending on which platform you're running it on. You can also set several environment variables that can help you in getting a lot of information, as you can see in the image below. So here are some examples on how you can debug JavaScript code using LLDB on a Linux machine. Now, what is JSL? So JSL is the simplex object class in JavaScript. Each object which is allocated through JavaScript is actually wrapped into a JSL structure. There are 8 bytes header for every object that denote several properties about the object. And why this is important from an exploitation point of view is that whenever you want to fake an object in JavaScript, you need to add valid headers, right? So one of the important things in the JSL header is the structure ID, which determines the indexed into a structure ID table. Now, why this is important is that whenever you want to fake an object, you need to guess a valid structure ID. And without guessing that valid structure ID, you will not be able to create a fake object. So in the old WebKit, the structure ID used to be incremented by 1 whenever you add a new named property. And this was useful for several exploitations because you can just spray certain properties and then guess a valid structure ID. However, with the new WebKit, there has been structure ID randomness added to the WebKit, which means that the bottom 7 bits of the structure ID are now randomized. Now in order to create a valid fake object, you must leak a JSL header using some kind of exploit primitive, and then use that to basically fake an object. So nowadays, as we discussed, the structure IDs and randomize, and hence leaking the JSL header is important in creating valid fake objects. So in this case, you can see that you have an object called person, and the JSL header is located at this address. So in this case, you can see that the address of the object is 4080, starts at 4080. So the JSL header comes at the very first. Now you have certain indexing types for arrays as well. So for example, depending on what objects are present in the arrays, there will be an indexing type for it. So for example, if you just create an empty object, empty array, the type would be array with undecided. If you have only integers, it will be array with int32. If you have an integer and double, it will be array with double. If you push an object as well, it will be array with contiguous. Yeah. Now coming to JS value, we already discussed what is JSL. So what is a JS value? So many different kinds of values are handled by the class JS value. So if you look at inside the file JS value.h, inside the folder, inside the WebKit code, you will identify a lot of different types of objects that it can handle. So for example, it can handle a pointer, a double, an integer, etc. Now, how does it find out whether it's an integer, pointer, or double? The highest bits determine what type of an object it is. And this technique is called NAND boxing. So you can see that a pointer will usually have the first 4 bytes set to all zeros, right? For integer, it will be all Fs here. Anything in between will be a double. Now you can try it out yourself. So for example, in this case we are creating an array with certain objects, right? And we will look at the address of the butterfly. Now what is a butterfly? We'll look into it later, but what we're doing here is that we're examining the memory starting from the object. And now the first value is actually all f's in the beginning, which means it's an integer, and the value is 1. Okay, and similarly by following the description provided here, you can find out that this is a pointer to the string, because as we discussed, if there's a string, then it will be stored as a pointer, and the pointer usually has the first 4 bits set to 0, right? So if this is actually a pointer to the string. And similarly you have the float, which is, as we discussed previously, stored as unsigned long int. And then we have specific values for Boolean statements. So for example, false is 6. You can also see over here that false is stored as 6 and true is stored as 7. Every object in JavaScript core is a JS object in a way. It has a mandatory butterfly pointer and can also store inline properties. So as we discussed before, that we can use the describe function to find out the address of an object. Just next to it lies the butterfly address, which points to a memory region, and to the right of the memory region are the elements, and to the left are the properties. Just before the properties, you have something called the length, which stores the public and the vector length of the object. So you can try it out yourself. So you can define an object A, and you can assign some named properties to it. And when you go to the butterfly address, which is 4028, so if you go to the 4028, you will see just on the left of it, it's the public and the vector length, and then to the left of that is the first property, which is 4, and to the right of that is 5. Now to the right of the butterfly is the elements which were stored previously. Now if there are no index properties in an object, then the values are stored in line. For example, in this case it's an empty array. It doesn't have any index property. It only has name properties. Then the values are stored just to the right of the object. So in this case the address is 4080, which points here. Now this thing, the first thing is the JSL header, followed by the butterfly, which is nothing. So in case there are no index properties, then the butterfly is 0, right? Followed by the value 1 and 2, which are the named properties for that array. Okay. Another thing you need to note is boxed and unboxed arrays. So the unboxed arrays are basically arrays that only contain double values, whereas the boxed one are one which contain double as well as object. What you need to know is that in case it's an array with contiguous, which means it's a boxed array, the value, this particular value is added to the double. We can also see that over here, you can see that a 64-bit integer addition of the value to the or 48 is added to the number. Okay, in case this is a JS object, which means it's an array with contiguous. Okay, now let's discuss what is a compiler versus interpreter. So an interpreter is quick to get up and running, and since we don't need to do any compilations. However, if you have code which is repeated several times, you still need to interpret it every time, and that will cause some kind of delay. It's suitable for JavaScript since it provides on-the-fly translation, whereas a compiler takes time initially to go through the compilation. During the compilation, it makes certain optimizations to improve the performance, and this is suitable for repeated runs of the same code. Core, you have a 32 MB read executable JIT region, and there are several tiers of execution when you want to execute JavaScript code. The first one, only the first one is the interpreted one. All the other 3 ones are compilation. So what is JIT? What does just-in-time compilation means? So just-in-time compilation means the compilation happens during runtime rather than prior. The way it works is that the JavaScript bytecode is compiled into machine code by the JIT compiler and then later executed by the JavaScript virtual machine, or the Java virtual machine, sorry. The code is monitored as it's running, and it sends the hot codes path to be optimized. So what this means is that if a function is executing several times, then it will be sent for optimization. And the kind of optimization depends on the tier of execution. So there are 4 different tiers of execution, and the higher the tier, the higher the compile time. However, the best throughput would be achieved with that. So for example, if we have a function which is getting executed, let's say 100 or 200 times, it might be sent to tier 2. But if it's now executing 1000 times, so it needs more optimization. It will be sent for tier 3, and for more, it will be sent for tier 4. So the higher the tier is, the higher will be the compile time, because the JavaScript code will try to do as many optimizations on it as it can. However, in the end, it will lead to the best throughput. The way the optimization work is, one of the ways is that it works is that it starts to guess the types of the object. So for example, if there's an array which is getting called which has let's say a string, then and it's concatenating some other string, then JavaScript code will not check, let's say remove the type checks for that string, right? So it will just assume whatever input it gets is a string. So it's in a way assuming the type of that object. Now, since it's now removing the check for that specific type, this can cause several security issues, and it gives rise to a specific category of vulnerability which is called type confusion. Okay. However, in order to optimize the code, since we discussed, there are several assumptions which are being made, right? Such as, let's say, assuming types, or in also certain cases removing bound checks. Okay. These actions can be potentially dangerous and change the program state. And the JIT code might use the code without checking the type of the object, which might give rise to several type confusion vulnerabilities. This kind of an effect is called a side effect, because it's a side effect of optimizing the code. However, the WebKit developers are aware about these kind of issues, and they can break these assumptions using several operations, right? So assuming certain things are valid, or some things happen which are not expected, the JavaScript developers have written code that will break the assumptions and throw it back to tier 1. Okay. So for example, if there's a dangerous operation which is happening, the execution will remove all the assumptions made, and it would cause something called a bailout. Okay, and the bailout is usually done by calling a function named clobberworld. This breaks all the assumptions which are made by the compiler, and the execution is now switching from the compiled code to interpreted code. So you can see examples of clobberworld in several places in the WebKit source code. This is an example of the different JIT tiers. So what you can do is that you can attach LLDB to JavaScript core, then you can set this particular environment variable to true, and then you can have a file, let's say JIT tiers.js, which will have a specific for loop. Now what you need to do is that just change the counter on the for loop from 100 to 1000, and then 1000 to 10,000, right? And then see what the output is. So you will see that it's switching the tier levels as you increase the number of the counters. Now what is webcode? So the webcode is responsible for laying out, rendering, and displaying the HTML and SVG content on the browser, right? There in the past there have been several RCEs because of use after free vulnerabilities in the DOM. One of the reasons for this is reference counting bugs, where you are able to decrease the reference count of an object to 0 and then trigger a callback to that particular object, which will cause a use after free. The way the exploitation usually happens is by saving a reference on the stack, triggering a callback, a JavaScript callback to drop the reference, and then using that same reference to cause a use after free. However, in the past, there have been some recent mitigations which have made exploiting such bugs much harder. So some of the recent mitigations which have been implemented in WebKit are ISO heaps, GigaCage, bulletproof JIT, which is only applicable for iOS. Then you have structure ID randomness, and you have PAC, which is pointer authentication check, again only for iOS devices. So the idea for ISO heaps is that the idea is to provide separate heaps for different kinds of objects, because the way the use after free exploits work is that you are able to free an object and then overwrite it with another object of different type, right, which will allow you to do certain things. However, if objects of the same type are saved in separate heaps, this becomes much more difficult. So in this case, you can see that there's an ISO heap being created for the object type SVG element. Okay. Next, we have Giga 'Gauge' type, which basically prevents out-of-bound access. Now, what is Giga 'Gauge' type? Giga 'Gauge' type is basically prevents out-of-bound access. Now, what is Giga 'Gauge' type? Which basically prevents out-of-bound access. Now, what is Giga 'Gauge' type? Which basically prevents So it will basically prevent you from out of bound access vulnerabilities. And the way it works is that different objects are caged, and they're caged between something which we call runway. Now the runway, the size of the runway is the maximum value of an integer, which is 32 bits. What this means is that even if we have an out of bounds array access, the maximum value of the integer in the array, or the index in the array, can be 32 bits, right? So even if you can put a very big value on it, it will most likely end up in the runway between those two objects. Okay, so you can see several examples of different kinds of GigaCages here. So in this case, the primitive GigaCage is used for the primitive objects. The JS value GigaCage is used for JS value objects, and so on. Signing is relaxed for in iOS. The code signing is relaxed for WebKit by using the dynamic -code signing entitlement, which means that the code can read and write in the same memory region, read, write, and execute on the same memory region. So the previous exploit, what they used to do is that they used to write the shell code using the initial write primitive that they get, and then just jump to the shell code. However, in Safari, it does not host the JavaScript engine. Rather, as we discussed previously, the JavaScript engine is run in a separate web content process. In ARM v8, it introduced support for something called execute only memory protection, which means on certain memory mappings, the processor can execute but cannot read. And this was used to implement hardened WebKit. However, before discussing that, let's discuss what is a memcopy. So in memcopy, the first argument is the destination, which is the pointer to the destination array where the content is to be copied. Then you have the source, which is the pointer to the source of the data to be copied, followed by the third argument, which is number, which is the number of bytes to copy, right? So the idea of hardened WebKit is that you are kind of creating two virtual mappings of the same memory. One of them is executable and the other one is writable, right? And the writable mapping to the JIT region is randomly located. Okay, now what happens is that JavaScript core will emit a specialized memcopy, and in this memcopy the base destination address will be already hard coded. Okay, and then this memcopy would be made as execute only, and this specialized memcopy will now be used for all JIT write operations, right? So there's only a specific special JIT memcopy function which will be executed. Okay, now this means that an attacker cannot copy just call the memcopy function through its code. It needs to call that specific memcopy. Okay, now this can be mitigated using as I've already guessed, ROP attacks, which is return oriented programming, right? And this was in a way an early in a way this mitigation is useless unless there is like a control flow integrity present in there, and this was like an early warning for the attackers that control flow integrity is coming, right? So this is some code that is used to implement to basically emit that specialized memcopy. I would highly recommend that you check out E1 Christic stock in Black Hat on the link below. However, in the recent WebKit versions, it was replaced by APRR and PAC, which is pointer authentication checks. I would recommend you check out this talk again from Black Hat 2019. Okay, so what is an exploit primitive? So in computer science, a primitive is a fundamental data type that cannot be broken down into, let's say, more simpler data types, right? So the idea here is a primitive is something that lets you achieve one particular task and nothing less, okay, and nothing more. So in this case, you need to break down the exploitation strategies into different steps, which we call exploit primitives, right? So the first exploit primitive is that you need to achieve something called an address of primitive. Then you need to achieve the fake object primitive. After that, you need to achieve the read-write, arbitrary read-write primitive, followed by, let's say, a universal XSS or a sandbox escape. Let's say if you want to get the data from other tabs, you will probably do a universal XSS. However, if you want to execute code on the victim's device, you will be doing sandbox escape. And then finally, you go to code execution. Okay. Now, what are address of and fake object primitives? So the address of primitive allows you to find out the address of an object. The way it works is that whenever you store a JS object value, it is stored as a JS value, as we discussed. So what it stores is that it stores the address to that object as a pointer. Okay, Now let's assume that you kind of cause a type confusion vulnerability, and now this pointer is interpreted as a double. Now by reading that property, if you read that property as a double, you will be able to read this pointer value, right? So you're in a way able to find out the address of a particular object, and this is the address of primitive. Similarly, if you think about the opposite of this is the fake object, we are able to write a native double which is then interpreted as an object as a pointer using using the same type confusion vulnerability. When you're writing let's say a native double which is being interpreted as a JS value, you need to make sure that the double value is actually interpreted as a proper object. So for example, we discuss that the first 8 bytes of the object are the headers. So when you're writing a native double in your exploit, you need to make sure they are valid headers, right? One of the important things in the header was the structure ID. So you need to add a valid structure ID. So you cannot just write any native double. You need to have specific headers, and then based on what butterfly you want to add or what values you want to add, you will add specific doubles related to that, right? One important thing which I forgot to mention is that, let's go back to the butterfly slides, is that one of the most important things in an exploit is being able to manipulate the butterfly address. Let's say if you get some kind of primitive, we are able to modify the value of a butterfly of an object. What this means is that you have arbitrary read and write. Now what does it mean? How do I have arbitrary read and write? By just manipulating the butterfly address. Okay, let's assume if I want to read the address at a particular value, let's say x. Okay, what I will do is that I will set the butterfly value as x. Now what I'm going to do is try to access the first element of this object. Now when I try to access the first element of this object, it's going to go to the butterfly address, which is x, and then it's going to read the value from that address, right? So based on what value we put in the butterfly, we're able to read certain values. And similarly, the opposite of it is that you will be able to write values at certain places. So for example, if I want to write a value at the address x, I'm going to change the butterfly to x, and then I'm going to say x, I'm going to manipulate this object and change the first element to whatever I want. So let's say I say a of 0 is 2.5. What it's going to do is that it's going to go to the butterfly address, go to this address x which you want to write to, and then change the first value. So in this way we are able to achieve arbitrary read and write of memory. On to 2020, I highly recommend that you check out the write-up here. So the way this works is that it defines a function which calls the in operator on an array. Now the way the in operator works is that it returns true if the specified property is found in the object or in its prototype chain. Okay, then it calls this function several times, which does optimization in it. So by optimization, it does some kind of type assumptions on this object. Okay, then it assigns the proto object to the embed element. Okay, and then it adds an event listener for the event DOM subtree modified, and then it removes the embed elements. Finally, it calls this function. And now what happens is that when it calls this function, it finds out that the 100 index is not available in array, so it looks for the proto property, which means it looks at the embed object, okay, the embed element. And internally this calls the function append child. Once that function is called, the DOM subtree event handler is called, which instead changes the first index of the array object to this one, curly braces, right? So now this array is an array with contiguous, which means the address of this curly brace is stored in the memory of array. Okay, and now over here when it returns array 0, since there is type assumption that this array is just an array with integers, it just returns the first index of the array, which is not 1.1, but it's actually the address of this object. Okay, thereby creating an exploit primitive. Now, getting the address of primitive will also give you the fake object primitive. However, in order to create fake objects, you must be able to create valid headers. And one of the important things in creating valid headers is creating valid structure IDs. So in this case, the structure ID is leaked by making a fake function object and then calling the function.prototype.toString function on it. And the output will basically contain a function name which will represent the structure ID as a UTF-16 string. Then you can create a fake object using the leak structure ID, eventually being able to override the butterfly pointer of an object that you control, which, as we discussed, will give you arbitrary read write, right? So this exploit is very complicated to explain in a 40-minute hour talk. I would highly recommend you go through this link and read the write-up. Now, these primitives were actually first written by a known researcher called Samuel Graf from Project Zero. However, the Project Zero team has also found out the use of these chains or these primitives being used in the wild. Origin policy. So an origin is defined as a combination of a URL scheme, a host name, and a port number. The same origin policy in a way restricts which network messages one origin can send to another. Think of it as two tabs open in a browser and one tab not being able to access the data from other tab. And this is what same origin policy is, and it's actually implemented in the browser. Okay. So however, in WebKit, the value, whether same origin policy is implemented or not is stored in a boolean value, which is m_universal access. What this means that if an exploit can somehow get arbitrary read write within the render process, it can modify the value of this object. Okay, so this property is defined in the render, and since we have arbitrary read write primitive, we can override this value to 1. However, how do we find the place in memory where this value is stored? This can be done by dereferencing certain pointers and calculating certain offsets. Okay, so I would highly recommend you go through this code snippet mentioned in this link to understand how this particular exploit, which is written by Nicholas B, was able to use arbitrary read write primitive in order to change the value of the universal access property. So in this case, once this is disabled, you can in a way make cross origin request, right? So in this case, you have your code running on one tab which is able to access your Gmail data, which is probably open in another tab. Okay, so this thing is also known as universal XSS. Now, concluding with this talk, we can quickly discuss what is fuzzing. So you can actually fuzz JavaScript code as well. Two of the most recommended tools out there is Fuzzily, which is written by Samuel Graf from Project Zero, and Dharma, which is a grammar-based fuzzer. I've seen many people use their own grammars with Dharma, which turned out to be very effective. However, also you're welcome to try out Fuzzily. Both these tools are open source, so you can modify and write your own implementation on top of it. These are the list of bugs which were fixed in iOS 13.6. As you can see, WebKit to this day remains a very big attack surface, and vulnerabilities are being constantly found out in it and reported and fixed. So it's a very interesting area to get into these days. Some other things which we did not discuss today is how do we survive the garbage collector in case we have an exploit running. How do we actually find out the JIT region and execute the shellcode. We also did not discuss how we create our own shellcode. And we also didn't discuss how do we bypass certain specific challenges related to iOS, which is bulletproof JIT. We also did not discuss sandbox escape. Maybe in a new workshop sometime I will discuss all of these things. These are some of the recommended resources which I found very useful, and I highly recommend you go through them as well. Thank you very much for listening to my presentation. If you have any questions, you can contact me on Twitter or add me on LinkedIn, and I'll be available for QA after this talk in case you guys have any more questions.